So here we'll do an example about the least square approximation using the singular value decomposition. So let's say I have the following matrix. Yeah, so I have the following. This is a 6 here. Okay. And now we want to solve this least square approximation problem using the singular value decomposition. Okay. So recall that we will find some vector D which is equal to U transpose B, and in itself it's equal to D0 and D1. D0 only contains rows that have non-zero elements, and our solution will be given by solution C will be given by the matrix V of the singular value decomposition. So recall A equals U sigma V transpose times sigma hat inverse, recall, times D0. Okay, D0. So let's do that. So we'll find the we will in this case here we will find we will first find a transpose, because it will be easier to solve in this way, even if we would get a smaller matrix if we do it the other way, but here we will do it that way. So we will find the eigenvalues of A transpose, and so for that we will solve using the determinant. So we will find the eigenvalues, and so if you solve that, so if you calculate A transpose, first, so A transpose, if you calculate it, you should get 36 0 0 0 0 0 0. Okay, 9 9 negative 9, sorry, negative 9 and 9. Okay, so it seems easier that way. So if you find the eigenvalues, you will find it will give you the following: lambda squared lambda minus 72 times lambda minus 18. And so our eigenvalues will be lambda 1 72, sorry, lambda 2 is 18, lambda 3 equals lambda 4, it's equal to 9. Okay, and so here we have done A transpose, so we will find the matrix U of the singular value decomposition, and so if you solve that, you get the following eigenvectors. You get that U1 is equal to 1 over square root of 2 times 1 1 0 0. u2 is equal to 1 over square root of 2 times 0, 0, 1, negative 1. u3 is equal to 1 over square root of 2 times negative 1, 1, 0, 0. And u4 is equal to 1 over square root of 2 times 0, 0, 1, 1. Okay? And so here they are of length 1. Yeah. And so we can now find the vectors of V using the fact that V1 will be equal to 1 over sigma 1 times the matrix A times U1. And so we will get 1/3 times negative 1, 2, 2. Okay? And V2 will be equal to, if you do the same thing, 1 over sigma 2 times A times U2 to give you 1/3 times 2, 2, negative 1. And now we have only two singles value, which are the square root of 72 and the square root of 18. The two other are 0, and we can't divide by 0, so we can't use that formula for the third vector. Okay, but what you need basically is a third vector V that is orthogonal to the two others. So here, because we are in 3 dimensions, we can use the cross product. We could also use Gram-Schmidt, but here it's better to do it with the cross product. So we will get, if you do the cross product, you get 1/9 times 4 plus 2, which will be 6. 4 plus 2, which will be 6. Or theta I make. We rewrite it. Sorry. Negative 1. Alright, so we just calculate that. So that's negative 1 here. So. Negative 2. Is that correct? Yeah. Yeah, so you get a negative sign here, then you get 4 minus 1, which is 3, sorry, I did a mistake. Then you get negative 2 minus 4, negative 6. So this simplifies to 1/3 minus 1 minus 2, 1 minus 2. And it's already of length 1, if you can see it. And so this is our third vector. Okay? And basically what we could do is if we invert all signs, it doesn't really change something. So we could as well take the vector 1/3. We could even remove the third if you want. We could choose the vector 2, negative 1, 2. Okay, so it's just in the opposite direction. Okay. Now, so we have all our vectors. And now we could just write our matrices U, sigma, and V. So U will be 1 over square root of 2 times 1, 1, 0, 0. So you just put all your eigenvectors together. 0, 0, 1, 1. Okay. Your matrix sigma, it will be of the same size as your matrix A. It will be a 4 by 3 matrix. Okay. And its entry, so we had two eigenvectors 72 and 18, and the two others are zeros. So we'll get square root of 72, 0, 0, 0, square root of 18, 0, 0, 0, and 0, 0, 0. Okay, because the two last singular values are 0, we doesn't really even if the fourth element isn't on the diagonal, because it's 0, it doesn't really matter. And our matrix V will be equal to 1/3, negative 1, 2, 2, 2, 2, negative 1, 2, negative 1, 2. Okay. Now we can find D, which is given by U transpose B. So if you calculate that, remember B is given by 3, 6, 3, negative 3. Okay. And U transpose, you just take the transpose. So if you calculate that, you get 1 over square root of 2 times 9, 6, 3, 0. Okay. And so D0 will be 9, 6, and 3. Okay. You only take the rows where there is at least one non-zero element. Where there are no zeros. Okay. And so V, remember our formula, C is equal to V times sigma hat. So basically, yeah, it's that. V is a 3 by 3 matrix. So we need 3 rows by sigma. Because the last row is 0, we can just ignore it, okay? Because we need to multiply it with V, but V has 3 columns, so we need 3 rows for sigma. And so our sigma hat will be the inverse. We can do it in the same way, or at the same time. So here we have zeros. Remember, the inverse is 1 over square root of 72. This is really bad. One over square root of 72, 0, 0, 0, 0, 1 over square root of 18, 0, 0, 0. Okay, so we just removed the last row because we don't need it. And our vector D0, it has yeah, it has 3 rows. Matrix sigma has 3 columns, so that's okay. Okay, and so if you compute C equals B sigma hat inverse D0, you get 1/6 5/2 7 1, and that will be your solution for your least square approximation. Okay, so what you have to do is you find the singular value decomposition of your matrix first. You can choose to find the eigenvalues. You either choose A transpose A or A transpose. Here it was better to do A transpose. Okay, and so then we can find the eigenvectors of U because we choose A transpose, and then we can use the formula that Vi equals 1/sigma I. This is sigma times A times Ui to find the corresponding vectors of V. And if we don't have enough singular values that are non-zero, we have to find a vector V that is orthogonal to the 2 others. So here we use the cross product because we are in 3 dimensions. You can otherwise use Gram-Schmidt or another method. Then once you have found U and V, which are orthogonal, so your matrix sigma will be a diagonal matrix, almost a diagonal matrix. It's of the same size as A. Its diagonal entries are the square root of the eigenvalues, and then there are zeros everywhere else. And then you solve your least square problem. So you find D equals U transpose B, and also D is divided in 2 parts, D0 and D1. You only for D0 you only chose the rows that have non-zero elements. Okay, and then your solution will be given by C is equal to V sigma hat inverse D0, and so sigma hat basically that you consider you remove some rows that have only zeros to be able to multiply them with V. So you have the same rows in sigma as you have columns in V, and the inverse you just in the elements in the matrix you just do 1 over the singular value. Okay, so 1 over the singular value, and there are 0 everywhere else. Okay, and so it's like that you solve your least square problem. There's another way to do it, just that you know it. You can find some element yi, which is given by 1 over sigma I times ui transpose, so some vector in u times c. Okay, so you multiply your vector c with your one of your vector u transpose, and then you divide by the ith singular value, and then you get your ith element in the vector y. Okay, and then your solution. Sorry, here I made a mistake. C basically it's not the right. You multiply with B. Basically, in some books they use C. It's the same thing. Here our data that we have at the beginning is with B, and then your solution. So here we use C. Is given by the product of the matrix V and the vector Y. Okay? I hope I didn't disturb you too much in this video. This is another formula to solve a least square approximation. Thanks for watching.